Good morning, everyone. Thank you for inviting us. I'm Shunsuke Kurita from the Cockpit Lab. So today, I will share my experiments at CERN. So the photo in the background is from when I attended the experimental party, and the building is that where I was usually working. So I went to the CERN, which is a European research laboratory located on the border between the France and Switzerland. And I stayed there about for 2 months from 30th June and to the 3rd September. And so here is a CERN main site, and the red ring is a Large Hadron Collider, LHC. So LHC is a world's largest particle collider built by CERN, and the perimeter is about 27 kilometers, and it has several collision points on the rings, and above them is an experimental control room. So here I show the main LHC for experiments, Atlas, ARIS, CMS, and LHCb. I belong to the ARIS group. And the ARIS site is shown in the previous slide. This one. Okay, so before going to the purpose of my trip, I'd like to briefly explain the ARIS experiments. So ARIS is a collaboration of 40 countries and about 2,000 participants. And this experiment aims to reveal the properties of post-gluon plasma. So let's follow the data taking process of ARIS experiments. So first, LHC provides clockwise and anti-clockwise beams. And this is the LHC beam status. You can see the current LHC status starting by searching the LHC page 1. And then the beams fly at collision point and the particles are detected by the ARIS apparatus. And the readout rate is about 3.4 terabyte per second. So it's too much to store. So the data computation are performed on the online processing system, and then the data rate will eventually be reduced to 90 gigabytes per second, and then the data is saved to storage. So the purpose of my business trip is to participate in data taking shift, center shift, and onboard shift, and to develop the detector control system. So ARIS experiment has 3 control systems: detector control system, and experiment control system, and quality control. So first, let me talk about center shift. Center shift consists of 3 shifter and 1 shift reader. 3 shifter are DC shifter, EC shifter, and QC shifter. In this day, I took the DC shift. So they are the center shift member when I took the DC shift. The main role of the center shift is to handle and monitor 12 detectors. And the DC's task is to manage the detector status according to the LHC beam conditions. So the beam energy of LHC is so intense, so powerful. So the ARIS detectors must be kept safe during the beam tuning. And we have some error. We take action to resolve it and maintain the good detector conditions. So, for example, we perform the function from the DC shift panel made by DC's expert. And if the issue requires expert intervention, we call the on-call shifter and solve the problem. So as an outcome from the shift, I, I was able to make new acquaintances. We are talking about each other's background and research topics. It has increased my knowledge and helped me in my own research. So in particular, I'm collaborating with Jonas, who was a shift leader, on developing new frameworks. So and currently I'm working with him on the implementing new detector information into the analysis framework, and it will broaden the scope of the analysis for other analyzers. So next second, I will talk about on-call shift. So there's one on-call shifter for each subsystem, and so and the we the on-call shifter the responsible of on-call shifter is less than central shifters, but we need to control and monitor all of the everything related to the subsystem. So, and I was in charge of the MFT on-call shift. The main role of the MFT on-call shift is to monitor all activities related to the detector and respond to issues. According to the on-call shifter instructions, on-call shifter must be available and operational 24/7 and be aware at any moment of MFT, RX, and LT status, so that on-call shifters are expected to be available to respond to on-calls even while showering or sleeping. So it was not easy, but was a good experience for me. This is because I could gain a deep understanding of data taking process. So when I was a central shifter, I experienced the difficulty of grasping the large-scale experiments as a whole. But I also realized that the on-call shift is one of the best ways to understand the overall data taking workflow. Okay, so let's move on to the developing the detector control system, DCS. So DCS development refers to develop the panel that central shifter and on-call shifter use. This is an example. So there are the types of DCS interfaces. So from left to right, this is the central shifter panel, on-call shifter panel, expert panel, and expert CUI. So the central shifter panel is very simple, but has limited functionality. So on the other hand, so expert CUI panel is complex, but be able to handle everything. So my main role is to add new function and implement user-friendly DCS panel from here to here. And it will improve the smoothness of data taking operations and will reduce the human error. So I will share one example what I've done during this day. So it's implementing one chip exclusion panel. This is a MFT detector, and this illustration is a disk face of MFT. And green chips is a state of active and ready. White is not active, and orange is active but in error. So data taking quality becomes medium or bad when some chips in error. So in this case, we perform the power cycle and the chips recover. But some chips will be back in errors immediately. We call the chips is noisy chips. So in this case, we want to easy switch their active state to active from active to deactive. So to achieve this, I plan to develop a panel to manage One is the chip state efficiently. So during the state, I discussed with the MFT DCS expert in person, and I create the one-check exclusion panel and some script. So one of the benefits of working on site is that direct discussion with experts accelerates this development. So the immediate feedback makes the implementation smoother. And it helps both DCS development and my own research. So let me summarize my talk. So during my stay, I was able to make a new acquaintances and discuss with experts in person. And these experiments led to extend the border of my knowledge and increase motivation for research. And I was able to carry out smooth and rapid thesis development. And finally, the budget was provided by the Overseas Dispatch Program of WPI-SKCM². So I'd like to thank Iwata-san, Yanaka-san, Mondo-san, and Dosha-san for their support. That is from me. Thank you for listening.